Hi, everyone. So my name is Tamir, and I'm going to talk about Android security and some new stuff in Android security. Basically, I'm going to start speaking about some Android security enhancements in general, and their background. I'm going to talk about Project Treble, the topic of this talk, a new security enhancement by Android. I'm going to talk about a vulnerability I found related to Project Treble. And lastly, I'm going to discuss whether Project Treble is actually a good security enhancement or not. So one thing I think you should note, like I know Android Pie, Android 9 came out 2 days ago, but still, like this switch was done on Android Oreo, but it's all still completely relevant. Okay, so before we go into details, a little bit about myself. My name is Tamir Zahavi-Brunner. I work in a company called Zimperium, where I do mostly Android research, Android vulnerability research. And I would like to use this point to really thank Zimperium for allowing me to do this interesting research and work with really smart people. Okay, so security enhancement. Let's start with a question. So by show of hands, how many of you has ever dealt with exploits? Be it in a CTF, challenge, exercise, whatever. Okay, nice. Still keep your hands up. And out of you guys, who here has ever dealt with a security enhancement? Nice. Okay, so you kind of know what I'm talking about. To mention it a little bit more, so we know by now that when writing code is written by humans. So we know that we can't prevent bugs. Humans obviously make mistakes, so you can't really expect to prevent all the bugs in the world. Instead, what we do is that we introduce security enhancements. Security enhancements are added as an extra layer of defense. They are there to basically do mostly either prevent bugs from turning into vulnerabilities or to prevent vulnerabilities from being exploited easily. So I have here some examples for very common security enhancements. I'm not going to go into every single one, but the important thing here is that Google really likes the security enhancement approach. They add new security enhancements in every major version. This is something they really do a lot. And one very massive security enhancement in Android is SELinux. Let's look a little bit into that. So this diagram I have here is actually, I think, similar to many operating systems in that you have the untrusted code, this time the application, and it wishes to perform a privileged operation. It doesn't have direct access to the driver, so it uses inter-process communication, IPC, in order to ask a privileged service to perform that operation. This, again, is a very common process, but here we have SELinux. So how is that relevant? Everything here, every application and every service are a process. SELinux allows you to apply a set of rules for each process, limiting what each process can do. This way, every application is limited by the same set of untrusted application, the same set of rules for untrusted application. But each service, because each service performs a different operation, each service has its own custom set of rules. And sometimes a service would have a very, very narrow set of rules. This means that if you manage to compromise a service, what you can do with that is limited. You're only limited to that narrow set of rules. OK, so this is one security enhancement. Let's talk about another example, but this time from the bug point of view. I'm going to start with the bug. So Stagefright, kind of going back to Android security history, a set of vulnerabilities published in 2015. So there was a whole talk about Stagefright. There's no point about talking about it that much. But the core issue here is that you could, through a single vulnerability, through a media file, which means completely remotely, you could compromise the media server process, which was very high privileged. You could get access to the camera, for instance, to the audio. Very dangerous, obviously something that Google wanted to defend against. So the first step was to fix the bugs, but then a more drastic approach was needed. Let's look at that. So as I mentioned in the first slide, when humans write code, you can expect bugs to be there. So media files are very hard to process, and they're very complex file format. So even today, so Stagefright was in 2015. This is from a bulletin from 2018 with similar bugs in the media file parsing code. Google knew, okay? They knew that they couldn't fight each small battle and really work hard and fix every single bug. That was just not going to be possible. So the approach they took is security enhancement. So it took them some time from Stagefright, but eventually they reached the media server hardening or separation. What you see here is in Android Nougat, Android 7, they decided to separate the service, the highly privileged media server service, into multiple processes. This way, the service in charge of processing media files is no longer very privileged. You can almost do nothing with that. So vulnerabilities like Stagefright no longer are that dangerous. OK, so up until now, I've been talking about kind of history stuff. But again, this talk about Project Treble. So let's talk about Project Treble. Maybe some of you heard about that already. Google discussed about Project Treble a lot in the context of Android updates. So Project Treble was introduced as part of Android Oreo, Android 8. And essentially what it does is that it separates between the AOSP, the Android open source project part, basically the core, the raw open source Android part, and the vendor part, the Samsung, LG, Nokia, their own code. This way, when you want to update, you can update only the AOSP part, meaning that updates are much easier. It also operates as a security enhancement. So this diagram here is also based on stuff that Google discussed. So basically, Google, after the separation in Android Nougat of Media Server, they noticed that there were still some services, single services with access to multiple drivers. So they wanted to perform similar separation for all of these services. And they actually combined that idea with the separation between vendor and AOSP part. So what they did is, like, as you can see in the diagram, previously you have a service with access to multiple drivers. But with Project Treble, it is separated. There's like what previously was one service with both vendor code and AOSP code is now a single AOSP-only service, and multiple vendor or HAL, hardware abstraction layer, services. And what you usually have is, for each driver, you would have its own HAL. This way, you no longer have a single service accessible to multiple drivers, and you have a separation between the AOSP and the vendor part. Also, worth noting, SELinux, again, is relevant here, because when you separate between what each service and each process should perform, the rules become, again, much narrowed. All right. This is an example of, services were separated in Android Nougat, and in Android Oreo, in Project Treble, they were separated even more. OK, so up until here, I've been talking about kind of background information. This is what Google talk about. Okay, this is from a Google presentation, this diagram. But I'm a security researcher. I want to research how stuff actually work behind the scenes. I want to really understand how they work internally. So I decided to look into it and basically research how Project Treble really works. So in order to do that, I decided to pick a single service which went through Project Treble modifications. I picked MediaDrmServer. So MediaDrmServer, in short, it is in charge of helping applications decrypt DRM encrypted media, like Netflix. And in order to do that, you need to have access to the T, or trust zone. So I'm not going to go into that. You can have a whole talk about the trust zone itself. But basically, you need access to the T driver. So again, you have this whole format of untrusted application contacting a service for access to the T. So this is how it works. But still, this is kind of wrong, because as we said, Project Treble came into place. The services were separated, and you no longer have a single service. You have the AOSP service and the vendor service. OK, cool. Now let's go a little bit deeper and talk about real technical stuff in how MediaDrmServer operates. So this is how the decrypt method of MediaDrmServer. And let's talk a little bit about the input that the decrypt method receives. The decrypt method is in charge of decrypting encrypted data. So the input, and this is a little bit complex, so bear with me. So first of all, the decrypted data can be very large. It can reach hundreds of megabytes even. So you can't really write all of that through the IPC mechanism. That would take a lot of resources and be very costly. Instead, what they use, and this is used in many services in Android, they use a feature of the operating system called shared memory. The encrypted data is on the memory space, in the memory space of the application, and the application simply writes to the IPC mechanism a reference to that area in its memory. The service can then use that reference in order to map the same memory area to its own memory space and have instant access to the encrypted data. And after it writes the decrypted data into that same shared memory, the application again will have instant access to that decrypted data, making everything much quicker. So some data that does pass through the IPC mechanism, there's some metadata, as you can see here, about the source and destination buffers, basically indicating where the encrypted data is on the source buffer and where the decrypted data should be written to, the destination buffer. One thing you should note is that the HAL service is the one who actually performs the write operation and writes to the destination buffer. So this is how the decrypt method operates normally. One more thing, I mean, again, from a security researcher point of view, to make stuff a little bit simpler, you can actually send a flag here that indicates that no data is encrypted, but rather the data is clear, meaning that the HAL service would simply copy the data as it is from the destination, from the source buffer to the destination. OK, cool. OK, so that's all the information about the input format. So what we have here, when you think about it, is a copy of data between this one buffer to another based on our own input. This is an interesting place for vulnerability research, right? You have a copy of data between buffers in a privileged service. So I decided to really take a good look into that and into the validation code. Because if you think about it, if they miss something in the validation for the input before the copy itself, then you might have an out-of-bounds read or an out-of-bounds write. So yeah, I looked at all the validation code, and I looked, and yeah, I found nothing. Yeah, and that's it. That's the talk. No, I'm kidding. So I actually found something. This interesting line, or rather, this interesting missing line. So let's explain. The highlighted line here is actually a perfectly fine validation line. So what happens here is that another input parameter passes to the IPC mechanism, which is the size of the data, which is separate, like it's separated from the size of the source or destination buffer. It's another completely different input parameter. This means that the service would have to verify that the size of the data doesn't surpass the size of the source or destination buffers. So this line basically verifies that. It verifies that for the source buffer, the total size here is the size of the data. And this line verifies that total size is less than or equal the size of the source shared memory. But there is no similar line for the destination buffer, which means that, let's say, we send the service a very large source buffer with a lot of data and a very small destination buffer. What would happen here is that the HAL service would attempt to copy all the data from the source buffer to the destination buffer, essentially causing a buffer overflow, kind of a classic case of a vulnerability. We can overwrite data in the HAL memory space, the HAL service, outside the shared memory with our own data. Again, data completely under our control. You know, kind of a classic buffer overflow vulnerability. So yeah, success, fun vulnerability. OK, so yeah, that is very cool. But Again, this talk is about Project Treble and security enhancements. So how do they come into place? So I actually looked at it, and one of the first things I noticed was how stuff like Project Treble kind of changed stuff here. So before Project, okay, let's think about this. Project Treble actually modified how the whole chain operates here. I mean, if you think about it, a whole new process was added to the chain. The new vendor process, everything was modified. The whole code was refactored. One of those changes was how the inputs were structured. Before Project Treble, you had one buffer, basically, which contained both the source and destination, which means that the encrypted data would be overwritten by the service with decrypted data. But in Project Treble, they separated it into two different buffers, but forgot to add the check for the destination buffer. And this essentially caused a vulnerability. But now this is a little bit strange because, okay, you're thinking, wait, Project Treble is supposed to be a security enhancement. It's not supposed to introduce new vulnerabilities. It's supposed to remove them. So weird. But okay, maybe they missed something. They didn't spot that. Can you really blame Project Treble for that? So actually, okay, I took a very good look at the code that was refactored because of Project Treble, and there were many other issues. Yeah, the vulnerability was a little bit hard to spot, but some of the stuff here, I spotted them very easily. This really led me to the belief that maybe this code didn't receive enough attention. Because I think that perhaps if a developer would have looked at least and found one of those issues, the developer would maybe spend more time on the whole code and maybe even prevent the vulnerability. But then you could say, all right, so MediaDrmServer wasn't refactored properly. Is Project Treble to blame here? So this is a list of vulnerabilities, not in MediaDrmServer, but rather in other services, all similar in the way that they were all introduced because of Project Treble refactoring. So this kind of raises the question, was the whole refactoring, was enough attention put into the whole refactoring? And kind of leads me to the final conclusion of this talk, which is the answer to the question, is Project Treble a good security enhancement? So my answer is actually yes, but, or yes in theory. So, well, the way Google described Project Treble, in theory, yeah, it's good. The whole process separation, very nice. And it actually benefits security as it is, right? But I believe that the actual implementation here was neglected a little bit, as you saw with all the vulnerabilities and stuff I discussed, which, and it's kind of important. Because, in order to, yeah, it's kind of important to really invest in the implementation as well. Because I kind of, it makes me think at least that maybe Google were a little bit too keen with the whole announcing new security enhancements, and yeah, we have Project Treble, it's so sophisticated, we need stuff and that, but they didn't invest time in its implementation. So to sum it all up, my final point here is that I believe that in order to really have good security, you need to have good code quality as well as security enhancement. Yeah. So yeah, that's it. I would also like to use this opportunity to thank some friends and colleagues who helped me with the research and presentation, specifically Sneha, my BSides mentor, who really helped me a lot throughout the presentation, so thank you very much. And also some references in case you want to read some more technical information about the vulnerability. Okay, yeah, that's it, and thank you for coming.